So we are back in business, and last week we stopped on discussing the properties of a gas, and by looking up at a very simple model of free particles moving freely within a box of a certain volume, I was able to convince you at least that and I'm briefly repeating the calculation, that the average kinetic energy of the particles in the box can be related to the temperature appearing in a phenomenological equation of state for ideal gas. And therefore, I derived this formula, which you might remember from the high school, that the mean kinetic energy for a particle in a gas is actually basically a temperature multiplied by a coefficient Kb, which converts the temperature into energy. It's a Boltzmann constant. And there is a factor 3/2, which comes from the fact that the particles can move in a three possible directions. As we say, it has 3 degrees of freedom, and each degree of freedom carry with it a 1/2 of the Kb times temperature of the energy. That was for the gas, and we can use that knowledge to understand why it is very often said that the temperature is just the kinetic energy of a particle. Remember that we had introduced a concept of a temperature via the zeroth law of thermodynamics, or by a concept of a thermal equilibrium, that if we have many particular systems which are in a thermal equilibrium, then we can assign to this notion of a thermal equilibrium a number which we call a temperature, and that is a reading of a device which we use to prove that all those bodies are in the state of a thermal equilibrium. So imagine that we have a certain set of bodies, and we use as a thermometer a device which is an ideal gas. Then all of those systems are in a thermal equilibrium, and we assign as a temperature, T1, the reading of our thermometer, which is now the ideal gas. Since we know that the mean kinetic energy in the ideal gas is just the temperature, then we can say that this temperature T1 we assign to the system being in a thermal equilibrium is a kinetic energy of the particles, but not necessarily kinetic energy of the particles out of which these 3 yellowish bodies are constructed, but as a mean kinetic energy of the particles in our thermometer. So if we have another set of bodies which are in a thermal equilibrium, and we again use an ideal gas as a thermometer, and when it is brought to the thermal equilibrium with these bodies, the reading will be T2. That will be again a temperature, a mean kinetic energy of the particles of that ideal gas. So that is a simple-minded proof that the temperature which we assign to these bodies being in a thermal equilibrium, this phenomenological notion, is of a microscopic origin, and that is related to the kinetic energy of the particles in the thermometer, which is ideal gas. And since kinetic energy cannot be negative, because it is an average sum of a squares of a certain number, an average number of a squares cannot be a negative number, that implies that this temperature defined that way cannot be arbitrarily low. It must, at the lowest value of this temperature is 0. And that therefore we have established in a very elementary way a notion of an absolute temperature, and the absolute temperature starts with 0 and goes up, and the scale of that temperature is completely arbitrary. And the physicists decided that it is convenient to use this scale, compare the scale of those, the absolute temperature scale of, by the way, it's usually called the Kelvin scale, with the Celsius scale, which we use in, at least in Europe, for practical purposes. And therefore, the 0 Kelvin happens to be on a Celsius scale a very low negative number, minus 273 degrees Kelvin. So that is the how we can understand the fact that the temperature cannot be negative. Actually, the physicists occasionally use the notion of a negative temperature, and you might have heard the statements that some commonly used devices like lasers are systems which exhibit the negative temperature, but that is related to the fairly complex concept of what happens when the system has a finite number of degrees of freedom. And I'm not going to bother you with this very important, but the detail, in fact, although it plays some role in the very important in biology and also in medicine device, in the construction of that device, namely in the nuclear magnetic resonance machine, but we will be talking about later and without touching that concept. So we have a thermometer, and the question is that in order to measure the degrees of Kelvin, we have to have some model. Which will be something like the meters in Sèvres, close to Paris, which for God knows how many years, essentially until last year, was the fundamental unit of a meter, and there was also a fundamental unit of a kilograms and so forth. They all are gone, replaced by the fundamental constants of physics. Let me repeat: the velocity of light, mass of an electron, charge of the electron, and Planck constant, and the gravitation constant. But the question is that we have related all the other units in physics to those fundamental constants of physics, but we have a problem with the temperature, and still, if you want to have a good, we have to have a model of what is 1 Kelvin. You have to go to Gaithersburg, close to Washington, D.C., where the National Institute of Standards, formerly National Bureau of Standards, that's why the label on my picture says NBS. I'm sorry, NBS, National Bureau of Standards Kelvin temperature. And this is a drawing of a gas thermometer, which is the world standard of a temperature. I was extremely privileged to be allowed to visit to this device. It's a few floors underground in the main buildings of the National Bureau of Standards in Gaithersburg, and it's a long excursion to visit the thermometer, because you have to take a special elevator. There you have to a special thermal clothing and sit in the waiting room for quite a long time to wait for the equilibration of your external clothing with the very low temperature, with temperature is already in the waiting room around 0 Celsius, sorry. And then you are allowed to see from a safe distance this giant thermometer, and that is a historical drawing. People are working on a scale of temperature very intensively, and a few years ago, one of the heads of the experimental group working on thermometers in Gaithersburg, Mike Moldover, had suggested that there might be a possibility to replace the gas thermometer with another very interesting device, namely a very well made a spherical cavity, which is filled up with a noble gas like argon or helium, and kept at relatively low temperature, at a constant temperature at least, and where the radial excitation of a gas within the cavity will be excited. And since the radial oscillation of a gas, radial sound waves within the cavity are not damped by the viscosity, because it's no relative shear motion of the layers of the liquid with each other. And we remember from our lectures that viscosity is related with the shear motion of the two layers of the liquid with each other. So if there is a radial motion, there is no such a thing. There is a very tiny little viscosity, which is called the bulk viscosity, but it is extremely small for noble gases. So, and it can be taken into account in the calculation. So this radial modes is excited, and when it is in resonance with the size of the cavity, then we can measure the frequency of that sound mode extremely well, and the frequency can be calibrated with the fundamental constants of nature. Therefore, once we measure that frequency, we can set up the value of 1 Kelvin through the frequency, and the frequency is related to the fundamental constant. So we will be done with the model for 1 Kelvin. Unfortunately, that's the theory, and the problem, a technical problem, is that it is essentially impossible to make a so good spherical cavity that it will be better model for 1 Kelvin than the gas thermometer, this Kelvin thermometer in the NBS. No technical tricks allow us up to today to make a sphere so good that it will be a standard of a thermometer. So this is an open question for people with good engineering abilities to still work on building a good universal thermometer. All right. So having said about the properties of a gas, let's go on and discuss the properties of liquids. The gas was a system, as you remember, where the distance between the mean distance between particles was so large that we could have replaced the interaction between the particles via just collisions. When the density becomes in the system higher, then the distance between the particles becomes much lower, and it is not sufficient, it is essentially impossible to neglect the details of the interactions. And back in the 19th century, people developed a tool to describe the situation. So imagine you have a relatively dense system of particles which move at random, as is shown in this picture. These green arrows shows the velocity for a particular particle. And let's draw a little volume inside of that liquid, which has a certain small volume delta V. The script V will be used to describe the physical volume. And that volume is small as compared to the total size of the container containing our liquid, but relatively big, so there is plenty of particles of liquids inside. Such a procedure is called occasionally coarse graining. We split the system into the cells containing several particles, so they are, from the point of view of a particles, relatively big, but from the point of view of the macroscopic properties of a system, these cages, these little blocks of matter are relatively small. And then when we do this procedure, then the whole volume of the liquid will be split into these boxes, these red boxes, and each of those red boxes is located at a certain point R, where this point R is nothing else as, for example, a center of a gravity, center of a mass, or whatever actually we choose to be of any importance as a location. So our liquid has been mapped into the set of those subvolumes, which are positioned, labeled with some vector, radius vector R. And then we can count the number of particles in the volume delta R of that box, but the particles are moving. They have a certain velocities. So we have to now start to think about the system not in 3 dimensions, but in 6 dimensions, because each particle is actually moving or is visualized as a point, as an object in 6-dimensional space, the space which has 3 spatial coordinates, position, and 3 other coordinates which are components of its velocity vector. So in addition of splitting a space into those cells, which I have drawn here as red boxes, we also have to split the velocity space in the boxes, and each of those velocity boxes will have a volume delta V. Don't worry, in a real statistical mechanics, in the contemporary statistical and classical mechanics, we have to visualize the system not only in the 6 dimension, but in the space which is a 6 dimensions for each of the constituent particles times the number of particles. So it's a really huge, big space, which you might be exposed to that name occasionally, is called a phase space. And we have constructed this coarse graining of a space and velocity space into those little boxes. And now we can count how many particles are in that red volume with the velocities within the given volume in a velocity space. And the number of those particles is proportional to the volume of the volume in space and volume in velocity space. So it's proportional to the delta R and delta V. And there is a prefactor, a number, which obviously depends on the position, depends on the velocity, and depends only on time. Because a particle move, therefore they can escape from our volume or come in our volume. So that must be a time-dependent quantity. The function which sits here is called a one-particle distribution function. And this is a workhorse for constructing a theory which be good for systems like liquids. That function is occasionally called, I mean, it can be interpreted either as a number of particles in a given volume or as a probability that within the given volume delta R and delta V, we found the particles at the position R and V at the time t. These two interpretations of this function are essentially identical, with the minor problems which occur in a very fine mathematical details of the theory. So once we have that function, this one particle distribution function, then when we simply ignore, calculate average over the velocities, that function, which in mathematics is denoted as the integration, that is a moment where a few of the integrals will appear, but it's easy to understand. You have all the particles in a given volume, velocity volume, and then in order to have the density, we divided this by the script volume, and that script volume V is a volume of that red box, is a volume of the essentially red box times the number of red boxes, that is the volume of the container. So this is a normalization factor, and it plays a technical role that's really now of no physical importance. So if we integrated the function f over the velocities, we get the density of the liquid. And similarly, we can define the velocity of the liquid by integrating over all possible velocities, velocity times the function f. That is a vector, and this is an analog of this concept of a mean velocity we use discussing the gas. And I will introduce a third quantity, which is the mean kinetic energy of the particle. That is, if I integrate the function f, this probability of finding a particle in the place r with the velocity v at the time t, multiply the velocity square and sum it up over all possible velocities, and that gives me how much kinetic energy is stored in the system at the position r at the time t. As you see, these all quantities depends on the function f linearly, and we like to call these kinds of integrals, we like to call them moments of a function f. As you see, they have different geometrical meaning. When there is no v here, it's a scalar. If there is just one v, it's a vector. If there is a v square, it's again scalar. So the moments depends on how roughly speaking, those velocities, these powers of velocity, this is a velocity to the power 0. Here is a velocity to the power 1. Here is a velocity to the power 2. So there are this is a higher moment than this one, and this moment is a higher moment than this one, and the geometrical meaning depends in how we multiply the velocity vectors. So in a kinetic description of liquids, we had to use a concept which I called capital M with the label N, moments of a distribution function f, and this is just the function f, multiply by the n powers of a velocity and integrated over all possible velocities. So these are the basic concepts of the description of a liquid, and with this we can proceed a little bit further. And at the turn of the 19th and 20th century, there was a Viennese physicist, Ludwig Boltzmann. We already learned this Boltzmann constants K comes B, who was actually a father of a kinetic theory of matter in a proper mathematical formulation. He had been extremely active physicist. There are several other areas in theoretical and practical physics which carry the stamp of the work of Ludwig Boltzmann. Unfortunately, when the new physics started to be born, when Max Planck and Albert Einstein had turned the very foundations of the physics and built a new physics by introducing a quantum mechanics and relativity theory, Boltzmann was already very sick, and he had a brain tumor and committed suicide. There is an important place for the physicist, his tombstone in Vienna, and those who built up the monument there, they had written on the tombstone of Ludwig Boltzmann a formula which is very important in statistical physics, which unfortunately is a formula which has never ever been used by the Boltzmann, but somehow that is what actually happened. So what is the contribution of Boltzmann is what is called the Boltzmann equation. Boltzmann was able to argue that this function f, this probability of finding a particle in a liquid with the velocity v at the point r at the time t, obeys an equation. And that equation is a change in time of that function, which is a time derivative. And it is a seemingly simple looking, but extremely difficult integral differential equation, which Boltzmann had written. And what is very important, this equation can be derived in a systematic way from the very fundamental laws of classical physics, namely from Newton equations. If you will take the Newton equations for all the particles in a liquid, then there is a method. The method was essentially derived at the same, proposed at the same time by another great father of a contemporary statistical and physics, Joshua Willard Gibbs in the United States. And that procedure allows us to derive that equation. So this is an equation of motion. It's a Boltzmann equation. And having that equation, which is called the kinetic equation, we can calculate the equation of motion for the moment. Well, it is very simple. We take that equation, multiply both sides by the velocity and integrate. And we can get a set of equations how the moments change in time. And the right-hand side turns out to be, again, seemingly simple, but incredibly difficult. Namely, it's a certain nonlinear equation, and it contains not only the same moment, but also the next one. So as mathematicians say, we obtain a hierarchy of the equation. First moment is coupled to the second moment. Second moment is coupled to the third moment. Third moment is coupled to the fourth moment, and so forth and so forth. That we cannot solve. That is impossible to solve unless we solve the initial equation. And for many, many years, the exact solutions of the Boltzmann equations were unknown. And in the 60s, a Russian mathematician, Bobelev, was able to show few analytic solutions of a Boltzmann equation for a very particular simple situations. But in general, we cannot solve it, but we have to calculate solve those equations, because we know that the lowest order moments, the first moment is a density, the second moment is a velocity, the third moment is a kinetic energy. So we have to solve them if we want to derive a macroscopic laws which governs the liquid. And physicists have invented a procedure which is called which relates the n plus first moment of the particle distribution function to the previous moments, which I symbolically have written here. And that relation, which allows us to relate the higher order moments to the lower order moments, have a general name of a constitutive equation. And there is a tremendous amount of different procedures suggested by a physicist how to do this. And they go under different names. There is one procedure which is very much proposed by a distinguished group of physicists and mathematicians which call themselves rational mathematicians, and they claim that in order to have a good theories, you have to derive the constitutive relation or propose a constitutive relation for at least first 13 moments. And these are called the 13 moments theory. But there are much more simple theories. And today, we are in a better situation than our predecessors. Namely, we can completely forget about this whole business and take the particles. And once we know the potential, we know how they interact with each other, we can simply write the Newton equations for them and write a proper computer program and simulate the system on a computer. And that opens up a new branch of physics, which is called the computer physics. And we have the concept like a computer gases, computer liquids. And quite remarkably, the simulation of a real physical systems like the liquids or gases on a computer using the Newton equations, that is the only branch of physics where a new law of physics, unknown before that, was discovered by computer simulation. I'm not going to tell you what is. This is a slightly complicated. Perhaps I will make one word about it in a moment, but that is a comment which is worthwhile, namely the computer simulation of behaving of a real system is actually a spin-off of the nuclear bomb project, because the first computer simulations of many particle systems were done by the people who were constructing nuclear reactors. And actually this new law of physics has been found by two American physicists, Bernie Alder and Jim Reinhardt, who have been studying the propagation of neutrons within the core of a nuclear reactor. And they found that new law. When we look at the constitutive relation for low order moments, for n equals 0, 1, and 2, then we relate the density to the velocity and energy. And these are the hydrodynamic equations which we use, for example, to derive the Poisson law for the liquid flowing liquid through the pipes. And I would like to now to show you an example. Consider n equal 1. If we have the n equal 1, then we have to relate a first moment to a 0 moment of the distribution function. And that means that we have to write the relation between the velocity. I apologize that the vector is missing from the capital U. And this closing relation, the constitutive relation, says that the mean velocity U of R is proportional to the gradient of a density, that how the density changes in space, and divided by 1 over density. And there is some numerical coefficient here, which I have denoted as a number D. That I can rewrite for those of you who know a bit more of mathematics as a derivative of a log. But anyway, the U is a function of rho. So if we write the continuity equation, which was the first moment, 0 moment, that the chain of density, that is the first moment of F, a first moment of F is related to the first moment and to the second moment. Well, if we substitute this constitutive relation here, we obtain a very simple equation which contains only a density. That equation is called a diffusion equation. And this is probably one of the most important equations for those of you who study biology or medicine. This equation is also a fundamental equation in the fragrance business and in the cosmetics, as we will see in the few next examples. Here is to show you that a diffusion equation plays important role in biology and in genetics as a title of a paper from a journal Genetics, which says complete numerical solution of the diffusion equation for random genetic drift. Diffusion equation plays a tremendously important role everywhere in the applied physics. And it is also one of the, so the mathematicians have provided us with a tremendously powerful, as they used to call, codes for solving a diffusion equation for very complicated situations on the computers. And they also are doing it for, they apparently are also applicable in a really true biology. I had somewhere a paper recently for refereeing, which is about the diffusion used to improve the quality of the analysis of the pictures taken by the nuclear magnetic resonance, by the magnetic resonance machine for tumors, how the tumors spread in the brain of some individuals. I have no foggiest idea what is that, how to look at these pictures, but there is a considerable amount of mathematics in the paper, so that's my job to look through this mathematics. They propose a new code for solving it. It's a tricky business, and we shall see whether it's correct. All right. So we were talking about the viscosity. We were also talking about the random walk. Diffusion is a phenomenological description of the systems which, on a microscopic level, the kinetics is extremely simple. And we will spend a few minutes discussing that now. All right, so consider the problem of our drunken sailor, as we already said. We have a one-dimensional street in the city, and we have a particular individual who lives a bar at the point M, and with the equal probability, which is 1/2, can make a step right to end up in a bar labeled M+1, or left and end up in a bar with a number labeled M-1. And the distance between the bars is delta. All right, so the probability that he will make a step right is 1/2, and the probability that he will make a step left is also 1/2. So once he is in that point, minus 1/2, again he has a probability 1/2 of going left, or probability 1/2 going backward, and so forth and so forth and so forth. So the question is that it is basically not so much of interest to ask how many steps he makes, because he walks back and forth, back and forth. But we may ask the question, what is the region on this street he covers by doing a certain number of steps? And we calculate it is possible to calculate a square of what is the size of visited, how many bars he will visit during making n steps. And the result is that this average square of the distance he visited at most over that axis is proportional to the delta square. That is a centimeter square, so there must be length square, but it's proportional to n. So if we replace the number of steps by the time he spends to make one step, assuming, for example, that he always walks with the finite velocity, so that is then very easy to replace the n by t, we see that the square distance, average square distance, is proportional to the time and to some coefficient which I call d. The remarkable result of a kinetic theory of a solution of a Boltzmann equation is that this coefficient d here is exactly the same coefficient as appears in the diffusion equation on our previous slide. This is a picture which shows how the probability distribution of covering a distance x within n steps looks up depending on the number of steps. I put the sailor initially on the bar labeled 0. So in the n steps, the probability of a random walker is peaked around the bar. So on an average, he doesn't move from the bar, but he goes back and forth between these two places. And if n is 40, it's spread more and more and more. Those of you who ever learned it, this looks like a Gaussian function. And actually, this is the fact that in a one dimension, solution of a diffusion equation is a Gauss function, this Gaussian hat, this which you must have seen in many applied lectures, and that is the solution of the diffusion equation also in the one dimension. But the situation becomes complicated when our sailors will be not walking in a one dimension, but if he will be a virus. Now everybody talks about the virus. And he will be moving at random in the three-dimensional space. So in the three-dimensional space, the situation is more complicated because at each point, that object, virus, bacteria, can move with the same probability upwards, downwards, or leftwards in the three possible directions. So this is a computer-generated drawing of the random walk in 3 dimensions. It's done by the very useful program if you will be encountering in your work mathematical calculations. So you should consider getting yourself it costs few zlotys program, which is a computer available on all platforms, even on the cell phones. It's a device which is called Wolfram Alpha. It's a scaled down version of a giant computer program called Mathematica, which is a program for solving complicated mathematical problems, not only numerical, but also algebraical programs, doing integrals, sums, statistical analysis, everything. And I use it to generate a random walk in 3 dimensions. And that allows me to calculate a very important quantity, probability of return. In the 1 dimension, you remember that was a Gaussian function. So the sailor on average never left the bar. It goes back and forth and uses a lot of time makes lots of steps, but on average, its average x is equal 0. In the 3 dimension, he does not come back to the initial point at each step. And the probability of return is equal 0.34 and so forth. So with the probability, roughly speaking, 1/3, he can return to the bar from which he left at the initial. So let's solve a few problems with the random walk. Remember that the mean square is proportional to the number of steps. So the first example is we have an object which makes n steps, and let the delta, the size of the steps, be equal to 1 meter. So let's make 100 of steps with so then L, the square root of a mean of square of x, is equal 10 meters. The size of the area visited by the sailor is 10 meters, but he makes 100 steps. So that individual covered a distance of 100 meters just to visit an area of the size of 10 meters. And for the n number 10,000, so for when he does 10,000 steps, so he covers a distance of 10 kilometers, he actually covered only the area of 10 meters. So the diffusion is expensive for a sailor or for the objects which does the diffusional motion to cover a relatively small area. So let's calculate the time which is needed for a particle to diffuse through the region which has a certain range, which I labeled as an S. The number of steps is then the S squared divided by delta square. So if I multiply the n by a length of delta, I get S squared over delta. So the total time is just the S squared divided by delta divided by the velocity with which particle is moving. Well, it moves with a certain velocity, and I am making an assumption that for each steps, the particle moves with the same velocity v part. So let's see what numbers tell. For the atoms in a liquid, the average delta, the steps for a particle, how much it moves, is about a 10 to the minus 8 of a centimeter. And the particle velocity in the liquid is of the order of 10,000 centimeters per second. So the times to diffuse over the range of S equal 1 centimeter in a liquid comes out to be of the order of 2.4 hours. And that's, of course, the difference between the gas and the liquid. So let's do another calculation. For a perfume of air in air, the length, the perfume particles are much more heavier, so it makes the delta for them is of the order of 6.7 times 10 to the minus 6 of centimeter. And they move roughly with the same velocity, 3.4, 10 to the 4th centimeter a second. So the same time of a diffusion is over 5 seconds. So so that is the distance, in some sense, as smells cover from your the time needed with the smell of a perfume to be felt at the distance of 1 centimeter from us. So that is basically why the perfume business is all about. All right. So the diffusion in biology plays the role because it is a main mechanism via which biological objects perform what is called the transport. So imagine you have a pipe which is filled up with the particles which will be diffusing, and you have a different density of those particles. I try to draw it so there is a higher concentration on the left side of that cylinder and the lower concentration on the right side of that cylinder. The length along the cylinder I labeled X, and the concentration on the left side is C1. I'm terribly sorry, I have forgotten to switch off my my phone. And the concentration on the right hand is C2, and the distance between those 2 points I denoted as a little d sum dx. And the particles are diffusing. So diffusion velocity is just that distance dx divided by time. So if the velocity of a particle is v part, and the step it does is delta, as in our previous calculations, then the time is dx squared divided by v particles times delta. So that allows me to calculate relation between the diffusion velocity and the particle velocity. If delta was equal to dx, they will be all equal, like in a gas. But in a liquid, that's not the same quantity. So we now have all right. So we have related the diffusion velocity to the particle motion velocity. And I will now define a quantity which I call a diffusion flux. And conventionally, it's labeled by a capital letter J. And that is a number of particles per unit time which go with the diffusion velocity, and that is given by a velocity over 2. The factor 2 comes out from the fact that we have used an average diffusion velocity, which obviously is different at different points. So we are back to the same drawing, but then we calculate the diffusion of a particles from a region 1 into direction of a region 2. But on the same time, the particles are diffusing backwards. For there is no reason why the particle sitting here in the random motion will not go opposite chosen by us direction. So we have a flux from region 2 into the region 1, which is given by that formula. So the net flux, if I want to calculate the next flux from one of the regions into a second region, I have to subtract these two currents from each other. And then I, again, using this relation, I can write that the current, net current from a region 1, the richer in the substance current, into the region which is poorer in a concentration of power particles, is proportional to the ratio of a difference of a densities divided by that length times a certain coefficient. That coefficient is again our diffusion coefficient. The difference of a densities of a particle, concentration of a particles, divided by the region between them is what in physics and mathematics is called gradient. And that is the definition of a diffusion gradient. I had also written a formal mathematical expression, but you should not worry about it too much. So let's now do some simple calculation. This diffusion coefficient is a particle velocity times the delta divided by 2. And in our example number 2, the delta was of the order of, in liquids, of order 10 to the minus 8 centimeters. Particle velocity was 10 to the 4th centimeters per second. So diffusion coefficient we calculated turns out from that formula, turns out to be 10 to the 5 times 10 to the minus 5 square centimeters per second. Experimental measurement of a diffusion coefficient, for example, of a sodium chloride in water, the kitchen salt dissolved in water, how the kitchen salt particles diffuse in the liquid is of the order of 1.9 10 to the 5. So as you see, such a very simple, very crude model of microscopic diffusion gives not so bad number. So I think I have convinced you that if you will go over a more sophisticated kinetic equation analysis, these calculations are quite good. And actually the whole game of a kinetic theory of liquid is calculate this kind of coefficients like a diffusion coefficients, heat conductivity coefficients in charge system conductivity and so forth. The transport coefficients as are being called. And one important comment, the analysis done so far is so crude that it cannot distinguish well between what is happening in a one dimension and in a three dimension. Actually, all this analysis was essentially one dimensional in nature. And the problem is that the closing of the hierarchy of the moment equation in liquid theory depends on the dimensionality. The problem is that the lower the dimensionality, if the system is less than three-dimensional, there are new physical phenomena which occur in a system. Dimensionality plays the role. You have seen it in a drawing of a one-dimensional random walker. It was a beautiful curve. Everything was beautiful and symmetric. Probability of return was as expected. But when we have done the simulation in a three dimension, then I have shown you that it looks very much different. And the same is with the transport coefficients. And a remarkable thing is that in one dimension and two dimension, strictly speaking, transport coefficients do not exist. Closing of a hierarchy is a bit of more complicated in a low dimensionality than in a higher. All right, so that was a short discussion of a diffusion, and I would like to finish the discussion of the diffusion by discussing diffusion through the membranes. That is something what is extremely fundamental in biology. And we distinguish two different kinds of transport through the membranes. There is a passive transport, passive in a sense that no energy is required to generate the process. And usually, particularly biologists classify it into the simple diffusion, facilitated diffusion, filtration, and osmosis. And there are active transport phenomena where the energy is required to provide the energy necessary for transport. And the one is a primary active transport is provided by ATP. This is like a propagation of something over the molecular motors. I'm not an expert on it, but there's a problem how the molecules are being transported over the chain of other molecules forming biological structure in animals' bodies. And the secondary active transport, which the energy is provided by electrochemical gradients. This second kind of diffusion through the membranes is the one which is important in future car business, in assuming that the future communication will depend on the cars powered by the power cells generating electricity from the diffusion of electrons through the membranes in the device which is called the power cell. All right, so let's talk about it. Diffusion through the membrane, simple diffusion. This is the picture. I took these pictures from some biological literature. This is the axis of the time. We have a lipid bilayer, a cell membrane, and on the one side we have particles suspended in the liquid, and we are analyzing the process when these particles sneeze through the separating bilayer, and this is a process of a simple diffusion. So after a while, some of those particles will find its way to push around the particles and down there, and they find its way into intracellular space, and eventually we have a concentration of the blue particles on both sides of the dividing membrane. When this is happening, the important thing is that the flux, diffusion flux, is proportional to the concentration on both sides of the membrane, and the coefficient P is called permeability coefficient. So that is basically a very simple diffusion, but the diffusion coefficient to some extent is replaced by the permeability coefficient. The unit of a permeability coefficient, in contrast to the diffusion coefficient, which is centimeters squared per second, is just a centimeters per second. Well, now we are talking about the facilitated diffusion. And a facilitated diffusion is that we have, again, a biological membrane, for example, a plasma membrane. We have the extracellular fluid, some impurities, green objects, and there are special carrier proteins sitting in the membranes, which opens up a channel through which the diffusing particles can sneeze through, and they fill up the other side of a membrane. This is called the facilitated transport. The third one, filtration, is even more simple. We have the current of the liquid with a suspension, which comes to the membrane, and it just goes through via the holes and sneezes through. This is the process of a filtration. This is a verticular or a conventional or called dead-end filtration, and this is a tangential filtration where we have a wall and the particles are flowing along it, and since the particles, even if they flow along, they also have the velocities in perpendicular direction, then they also can sneeze through the membrane. This is the most simple of these three processes. And finally, we have the osmosis. Osmosis is related to the transport of the water. We have on the one side of a membrane, we have a water and the particles which diffuse in the water. We have a cell, and the cell has hydrophilic particles on its outside. And somewhere in that cell, there is a huge molecule called aquaporin, aquaporin. And aquaporin can take the liquid with the particles which are in it and transport it through the membrane, which is hydrophobic in its nature, and deliver to the other side. And this process is called osmosis. And the main role in that process is played by the particles, which is called aquaporin. Well, what you see here is the sculpture called aquaporin, which is actually a fairly good model of the molecular structure of an aquaporin, which is constructed by a Warsaw sculptor, Jarosław Kozakiewicz, and it sits in the front of the Copernicus Science Center in Warsaw. We are still shut down, but we hope we will be open soon, and then you will be able to come and see it in practice. All right, now we are going to talk about the solids. That will be a short introduction to solids. We will be continue further next week, but I will have to stop a little bit earlier today because I have another talk at 3:30. All right, solids. We remember our distinction of gases, liquids, and solids. And again, if we have a solid, we can distinguish between two basic kinds of solid: a crystalline solid, where the particles constituting the solids are sitting in the points of a space lattice, and amorphous solids, where the distribution of the particles is not governed by the laws of the geometry. This is another example of a difference between solids like the glasses and the crystals. And this is the same physical system, barium oxide, which can form a glass. And in a glass, this is a molecular construction, or form a crystal. And as you see, that's the difference. Because in a crystal, this cells are construction in a periodic spatial construction, which fills up the space. And in the glass, they are local, and these local cages are more or less randomly oriented. These are ionic solids. This is a kitchen salt. And as you see, these are basically two cubic lattices which are squeezed through each other. There is a one cubic lattice for the sodium and the other cubic lattice for a chlorium, and they are squeezed through each other to form the structure which is called the kitchen salt. The same structure is for not the kitchen salt, but for the similar objects. We have a metallic solids. This is an artist picture of a copper that explains the color. But in a metallic solid, in addition to the ions of a copper or ion or whatever sitting in a lattice points, then there is another component, electrons, which are moving freely within the lattice. And there is so many of these electrons, free electrons there, that a piece of that matter, as it has to be, is neutral, electrically neutral. And eventually we have a covalent network solids, like a carbon, the carbon, and that is a structure of a diamond. We have a similar structure. This is a silicon dioxide. But as you see, the bonding is very much different. There is a silicon carbide, which has yet another bonding. And eventually we have this newly discovered bonding of a carbon atoms, which form not a three-dimensional structure, but a layer of a two dimensions. This is called a graphite. And for quite a long time, the graphite was around us, but eventually Russian physicist Game had figured out that if you will take a graphite and paste to it a layer of a Scotch tape and tear it off, he will manage to get a single layer of the carbon atoms in a graphite separating from the rest of it, and he will generate a two-dimensional graphene. And that's how the graphene came into existence. It was the new material discovered by using a Scotch tape. And this is a two-dimensional crystal which offers this enormous technological applicability. So far, none of them has actually crystallized, except of one. And but anyway, so this is another kind of a crystals. And finally, we have molecular crystals. This is carbon dioxide. and this is a kind of crystal of iodine. So we have enormous variety of different crystals, and I have, and here is a table of the various crystals with the property, and with that I will finish our lecture today. We have ionic crystals, which consist of ions. They are bound by ionic bonds, and they are hard, brittle, conduct electricity as liquid, but not as a solid, high to very high melting point. And the typical example are the kitchen salt and aluminum oxide. Metallics are the malleable, ductile, conducts heat and electricity, and so forth. And there are copper, iron, titanium, lead, uranium, palladium, gold, and so on. Covalent networks are atoms of electronegative elements, are very hard, non-conductive. They are carbon, diamonds, silicon compounds. Molecular crystals are water, carbon dioxide, iodine, and alcohols, and many others. And the most important out of them is, of course, a crystal of the water. This is the ice, one phase of the ice. This is the water, the same atoms, the same particles of which are moving freely. And the ice seems to be a very simple structure. But because of the fact that it is held together by the hydrogen bonding, it appears in enormously complicated phase diagram. This is a true physical diagram of a water. And this brownish region is a region where I used to live. We are living on a very tiny, narrow area around this line, from the slightly to the left from freezing point to the right, slightly to the right over the boiling point, and a little bit above and lower. We have a vapor phase here. This is a solid liquid vapor triple point, and up here is a critical point, and here we have a solid. But we have enormous amount of different solids, and the ice has actually 19 different phases. So speaking about the ice, we are speaking about the one of the phases of the ice, which is 1H, label 1H around here, but we have much more of them. And as you remember, there's a one phase of ice, which appears in the Kurt Vonnegut book, Cat's Cradle, and we hopefully are not going to find out that phase of ice soon. The ice is a remarkable substance for other reasons, and it will appear shortly on our screens when we will be talking about the third law of thermodynamics, probably in 2 weeks. So I apologize, but I would like to discontinue for a day today, and as usually, I will provide you with the recording of this stuff in the days to come. So take care. Bye-bye.